Okay, so basically what have I written over here? I've written basically what I was talking about, Newton's second law. Newton's second law, but this is going from A to B, kind of Newton's second law. It says, okay, so what I was saying was, okay, you want acceleration, you better find force. And those, some of the forces better add up to something other than zero. But you also have to take into account the object's mass. Why mass? Well, because that's a measure of its inertia. What's inertia? It's resistance to acceleration. There's another way to think about mass, though, and since we're here, this has nothing to do with rotation, it's just a little review. Is there's another role that mass plays in the universe, and that is in terms of gravity. So basically, if you've got something with mass and it's on the Earth or some other large body, it's going to experience a meaningful gravity force, which you quantify by mg. So there's mg. Now, when we think about mass in this way, it has nothing to do with inertia. It has to do with the fact that all matter attracts all other matter, and that gravity force is directly proportional to the mass, I guess the product of the masses. And in this context, we think of it as gravitational mass. Again, this has nothing really to do with the topic, but I thought, hey, why not throw in a little review here? And so in this case, this would be inertial mass. Different roles for the same physical quantity. Okay, anyway, that was just an aside. All right, now this is Newton's second law, the way we've always thought about it. But now we want to think about Newton's second law for rotation or for torque. I bet you could come up with the format for it already because I've been talking about how many parallels there are between translational motion and rotational motion. We have acceleration, angular acceleration. We have velocity. We have angular velocity. We have displacement, angular displacement, etc. Back and forth. So, what do you think would be? So, we're going to have our equation here. And what do you think would go on the left? What do you think we're interested in if we're thinking about Newton's second law for torque in this kind of format? What is the analog in the rotational world to acceleration, translational acceleration? I hear you.
Accelerational radial, the angle.
Exactly. Angular acceleration.
Yeah, and then the force would change in torque.
Exactly. So then we would basically add up all the torques. And so just like for translational motion, you say, look, if you want something to speed up, slow down, or turn translationally, you better have a net force equal to zero. Well, this one says if you want it to change its angular rate of rotation, you better have a net torque that's not equal to zero. Now, on the bottom is going to go, here is inertial mass, or inertia, and you might think, well, M here, but that would be wrong. Okay, so that's one of the. So this is going to be rotational inertia, but it's going to be, another analog, which is that if you want angular acceleration, you need to find or need to create a situation where the net torque isn't zero, but then you also have to consider the object's own resistance to rotational acceleration. But it's not going to be, I'll just give you a little preview. It's not going to be M. It's a little bit more complicated than M. Okay, so the next, oh, let me point out also, there's another, okay, why don't we just call it rotational inertia? That's what I call it, but in the textbook, and I also call it this too, but it's called moment of inertia. Moment doesn't mean like a moment in time. It means really, it's associated with torque. It's another word for torque. So this is like inertial torque or torque inertia. And it has its own letter abbreviation, and it's capital I. Sorry, that's the way it is. New term, a new symbol, but it's going to be. But the way we approach angular acceleration and Newton's second law for torque is so similar. But there is this complication about rotational inertia. So this is what we're going to spend the next several minutes developing. This idea is, how do I quantify the rotational inertia of an object? With linear motion, translational motion, it's just what's the mass, okay? Here, it's a little bit more complicated. So we are going to look at something going around in a circle. First, okay, so I've got this object of mass m, and it's connected to the axis of rotation by a little lightweight rod. Think about this as a top-down view. So we have a table or something, and this thing, well, that would go off the table, but it's spinning round and round and round. Now, I want to first talk about circular motion and kind of review some of those concepts, and then we're going to kind of pretty much ignore it. But because I don't want to confuse this circular motion acceleration with tangential acceleration, which is what we're going to focus on. So let's just step backwards a little bit and look at circular motion. And let's just say this thing is going at some speed. Right now it has some speed v. Okay, let's think about what we learned in circular motion about acceleration and force. Centripetal force. Okay, so we know if something goes in a circle, it takes force, but well, let's say there's going to be some centripetal acceleration, and that we can quantify by centripetal acceleration is going to be v squared over r. We also know that it's going to take force. Make it wider. It takes force to make something go in a circle because it wants to go straight, right? It has inertia. And we can quantify that force using Newton's second law, which says, okay, centripetal force equals the mass times centripetal acceleration, or mv squared over r. Again, this is a little review, because I don't want to talk, because we're going to talk about a different kind of acceleration. But before we leave circular motion altogether, and we start talking about the tangential thing, which I'll draw another diagram to show you, is I want to relate the tangential velocity, which is this v, to the angular velocity. I want to basically relate the circular motion to rotational motion, because we're going to use that in just a moment. All right, so we introduced this following equation or relationship in circular motion, which is I can know the speed of this thing if I know the radius and the period of its motion, the time it takes to go once around, because this is just distance over time. Now, what I want to do is I want to relate that speed here to its angular velocity, and then, because we're going to need that, or at least we're going to need angular acceleration. So if I just add some parentheses, this is something, we don't really need this for today, but I thought it's a good review. Good. All right, if I just add parentheses, but do nothing else, it's the exact same relationship. But now I see, oh, 2 pi, that's the number of radians in a circle, and the period is just the time, and so this is angular displacement over time. Or we can say that and I guess, let me just put in a little t here just to remind ourselves, so this is the tangential velocity. There is no radial velocity, really. Okay, so this is going to be omega. Remember, omega is angular displacement over time. And again, if you don't remember, this is a review. Okay, now, we're not really going to be using this today, but this leads us to my next point is, I want to go ahead and develop this idea. Suppose this thing was speeding up and going faster and faster. Well, we didn't talk about that in Chapter 6. Chapter 6 was all about uniform circular motion, but I don't want to add another force here. I just want to make a new diagram. But suppose I did have a force right here, and I was constantly pushing it. making it go faster and faster. There would be not only, well, there'd be, I'm getting ahead of myself. There'd be tangential acceleration, which I'm going to put in a drawing, but also angular acceleration. So I just want to quickly derive, how do I get angular acceleration? So, you know what? I'm going to go ahead and make my second drawing because I'm starting to talk about it without drawing it, and that makes no sense. So I'm just going to basically take my same mass m. I'm going to go ahead and put an axis of rotation. I'm going to have it going around in a circle. Why is it going around a circle? Because I got this plastic or little lightweight thin metal rod or something like that. Now, that means I'm considering all the meaningful mass to be in this, you could think of this as like a little metal ball or something like that. And then, so this could be like a kilogram, and this is just a couple of grams or something, just a tiny bit of mass holding it in place as it goes around. All right, now, I was saying that, what if there was a force? So here's the force. Now, this could be like your finger. You could be pushing this around. There could be a little fan on this thing, or a little rocket motor or something, but there's something making this thing go faster and faster. Okay, so there's the force, and I'm going to call that tangential force just because it's tangent. Everything I'm going to talk about now is going to have tangent. And now I mentioned this idea that anything going in a circle has centripetal acceleration, but that's not what I'm talking about now. I want to talk about tangential acceleration. That if you exert a force tangent to the circular path at this point, this thing's going to speed up. And so there's going to be some there's going to be some tangential acceleration. So I'm going to add that here. Notice that I'm not talking about the centripetal acceleration. That's always going to be directed towards the axis of rotation. I'm talking about the tangential acceleration. Okay, now you can see why I want to relate this tangential acceleration to the angular acceleration this thing's going to have. Okay, I should have drawn the drawing first, but now it's drawn. All right, so we just want to, now we have this relationship. Now I want to relate it to, okay, how does the tangential acceleration relate to the angular acceleration? And this is what we're going to do here. So in general, I mean, this is what we're going to use here, this relationship right here. So acceleration, the tangential acceleration is going to be, it's just like acceleration that we've always known. It's not this weird center-directed acceleration that's v squared over r. It's just your normal going faster and faster acceleration. So that's going to be delta v over delta t. Well, think about if tangential velocity is omega times r, then hopefully you would see that, or just by the idea that delta tangential v is going to be delta omega, or change in angular velocity, times r. So that's what I'm just going to plug in here. Okay, so now I can relate, the goal again is I want to relate the tangential acceleration to the angular acceleration, because I'm trying to build this thing. We're trying to figure out, how do I quantify rotational inertia? Whoops, sorry. Okay, so now I just plug in delta omega times r over delta t. I draw some parentheses here, and I don't know if you remember, but change in angular velocity over change in time is angular acceleration. So tangential acceleration equals angular acceleration times r. And this is the one we need for today. Just a little review. And I know that was pretty fast. All right. Now, how do we get, sorry to keep going back, how do we get Newton's second law for torque? We're going to start out just looking at Newton's second law for this particular situation, because this Newton's second law doesn't work just for translational motion. I mean, it has to always work that if you're exerting a force on something, it's going to accelerate. All right, so what we're going to do is we're going to write Newton's second law for this situation, which is the tangential, let me just, somebody edit out all of my extraneous remarks like grunts and things. All right, tangential acceleration is going to be mass times tangential acceleration. That's Newton's second law. Now, what I'm going to do is I'm going to substitute in for tangential acceleration what it's equivalent to, which is angular acceleration times the radius. I guess I should add a little radius here. Okay, so tangential acceleration equals m times alpha, angular acceleration times radius. Okay, now what I'm going to do is just multiply both sides by r, which I am allowed to do using algebra. I can do anything to the left side that I want to, as long as I do exactly the same thing to the right side. Now, think about this, is what I'm doing over here on the left is I'm taking force and I'm multiplying it by the distance from basically that r vector, right? This is like the seesaw version where this is 90 degrees. So what do I get when I take a force and multiply it by its distance from the axis of rotation when those two vectors are perpendicular? Rhymes with
Torque.
No, it doesn't rhyme with torque. It is torque. Yes, you're correct. That's torque. Sorry.
But torque
Yes,
kind of rhymes.
yeah, you got it. I'm being stupid. All right, so let me put the m comes down. Now the r times r. The r times r is r squared, and then we have alpha. So let's just put that in parentheses. This is Newton's second law for torque. This is the equation that relates torque and angular acceleration. But let's put it, sorry to scroll, let's put it in this format, and then we'll see if we can see what rotational inertia is. All right, so I've got, if you want angular acceleration, I'm just rearranging this to solve it in terms of angular acceleration, then, okay, I didn't include multiple forces here, but hopefully the idea is this isn't just torque in general, this would be the net torque. For example, I'm going to erase what I'm about to draw here, but if I had another force that was exactly the same as the red force, and it was keeping that orientation as it went around, you would expect to see no angular acceleration. So this can't be just any torque. This has to be net torque. I hope you buy that at least. Okay, so angular acceleration is going to be the ratio of the net torque acting on an object divided by m times r squared. Okay, now this is for a point mass. You say, what the heck is a point mass? This is a point mass. A point mass is something that basically is, its mass is all concentrated at one point. And in other words, this is one of the reasons why we don't want to consider this rod as having any mass. I'm going to erase what I'm about to write here. If we had like this object M and we had like a big thick board turning, okay, there's a lot of mass there. This would no longer be considered a point mass, where we could say the mass is all concentrated here at R. We'd have to kind of, so that's, and we're going to get to objects like this that aren't point masses. Okay, so this gives us some insight into what is rotational inertia. This is the rotational inertia for a point mass.
Mr. McIntyre,
Yes.
can you please elaborate briefly where we got r squared?
Yes. Okay. So I did this weird thing, which is I just multiplied both sides by r. So when I do that on the left, this becomes torque, and then I have this r times r here becomes r squared.
Is there a reason why you multiplied left and right side by r?
Yes, because I wanted to turn this into torque. Um, in the book, they have a slightly different
Oh,
approach.
yes, completely. Yeah, last week we learned that force times radius is equal to torque.
Yes, right. And this is like one of those seesaw type. This is where we don't have to worry about the sign of any angle. We don't have to worry about what part of the force is perpendicular, what part's parallel, because it's at right angles. Okay, so this would be for a point mass. What about, now I'm going to do something that's kind of weird because, okay, that's kind of useful if you have a ball on a string, but we want to talk about the rotational inertia of things like, again, I'm going to erase what I'm going to draw here just in case you are taking notes and you want to, but you're welcome. What about something like this where we have a board that's anchored here and we exert a torque? Or what about if we have a solid disk? These are not point masses. So how do we go from the rotational inertia for a point particle to something, that's not a point particle that has a distributed mass to it? That's our goal. Now, part of me says we should do a little sample problem here, but I mean, so if let's suppose that the torque was like 10 Newton meters. I'm just saying, how would you solve for the angular acceleration? Well, let's just not solve it, just make up some numbers here. Suppose this torque was 10 Newton meters of torque, and you had 1 kilogram, and you had 1 meter. You would just you would get, oh shoot, let's see, what are the units going to be? What are the units going to be? I think it's going to be weird looking. Okay, so let's make up these numbers. So if I have 10 Newton meters of torque and there's 1 kilogram of mass, and that 1 kilogram of mass is like 1 meter away, it's just like attached to a lightweight string or something that 1 meter long, and you're trying to get it to speed up, then this would be 10. And what would be the units? We'd have Newton meters over kilogram meters. No. Sorry. Newton over kilogram meters. And this is where I'm going to pause the video. Going. All right. So, well, I have Newton meters on the top and I have kilogram meters squared. So let me just do this. That's squared. That's what's, okay, so that goes there. Now, what the heck is a Newton over kilogram meter? Well, remember, inside of every Newton is a kilogram meter per second squared. That's this guy. And then underneath, I have a kilogram meter. Oh my gosh, what the heck does this come out to be? Well, kilogram and meter go away, and all I'm left with for units is per second squared. Now that looks bizarre, but I don't know if you remember when I said radians is not really a defined unit. That to me does not make a lot of sense, except we just write it in. So the technical units for angular acceleration is per second squared, which sounds weird, but this would be radians per second squared. All right, so here we go. Here's what we're going to do. We're going to kind of, there's my sample problem that I did, but I didn't think I was going to do. Okay, so let's get to this point where let's expand on this and get this thing so we can do rotational inertia for things like discs and boards and things rotating. Well, here's what we do. This is how we approach it. We are going to set up to where we have multiple point masses. So if you're wondering, I'm probably about 10-15 minutes away. So hang in there. All right, so this is going to look weird, because you don't really see many things like this. All right, so what we're going to do is we're going to put, there is our point mass. I'm just going to call this number 1, and so this is going to be R1. And then let's put another point mass, and let's make this a little bigger. This will be number 2, and then we can make up the values, and this is going to be R2. And then let's just have something crazy long here, and this is going to be number 3, and so this would be R3. And let's suppose that you or somebody else is exerting a force. Now, this has to be considered to be a rigid body. That means there's no meaningful deflection. There's no meaningful distortion. I mean, if these were wet spaghetti noodles, right? I mean, this would, that's not a rigid body. So these have to be rigid. So this thing rotates all at once. Every particle, all 3 particles have the same angular acceleration. Okay, so how would I quantify the rotational inertia here? Well, I'm just going to kind of try to ask you to think about it from a logic standpoint. Basically, all we need to do is each one of these has a certain rotational inertia, and so we're just going to add them up. So the total rotational inertia okay, there's a reason why we use symbols in physics, because this is I. Now, for our purposes, we could just, I mean, I can write the total. We don't normally write total. Okay, so what we're going to do is we're just going to add up the rotational inertia of each point mass. So what would be the rotational inertia associated with point mass number 1? Well, that would be its mass. Let's go to the formula. And again, this looks weird, I know. I mean, I thought inertia was just mass. Well, that's linear, translational. But for rotational motion, what this is saying is, I'm getting a little ahead of myself here, but basically is, we can, if we're talking about rotating objects, mass does matter. More mass will contribute to more rotational inertia. But it's also, where is the mass? How is the mass of this object distributed? Is all this mass kind of like right up against the axis? Is it kind of near the axis of rotation? Or is it spread out very far? And since this R is on the bottom and it's squared, you could see that the further out we put the mass, the harder it's going to be to accelerate this thing rotationally. All right, so basically m1 times r1 squared plus, and this would be, find another point particle. This, now we're up to 2, would be r2 squared, and then we would have mass 3, whatever it is, times r3 squared, and you would just keep going. Now, I didn't come up with any values here, but I mean, you could just make up values and you could get the rotational inertia of this entire weird looking configuration of point masses, and then the total mass would go in here. Again, that is, the symbol is I for rotational inertia or moment of inertia. There are actually a couple of mastering physics problems that are a little bit like this. Okay, now imagine that instead of having 3 point particles, you had hundreds and thousands and tens of thousands and millions. Okay, well, this is going to get a little bit weird here. But, so, well, sorry, I'm giving a little preview. Suppose that you had, I'm just going to start drawing a little crazy diagram. I'm not going to draw the radii, the R's. I'm just going to say, suppose you had a point particle there, and another one, and another one, and another one, another one, another one, another one. And the axis of rotation was, this is where it's all rotating about. Okay, I'm going to do this for like 30 seconds, and hopefully, oh my gosh, I'm going to start making my point particles bigger. See what I'm doing here? I'm just creating dozens. Oh my goodness. Keep going. Maybe you'll see what I'm doing here. Oh, I'm going to start making them bigger because, okay, all I'm doing is just thinking about, instead of having 3-point particles, I'm just having a tremendous number of them. But there's no limit. There isn't like, this rule is not limited to like, oh, you can add up to 8 of these or something like that. No, you can have thousands and thousands of these things. And does anybody guess what shape I'm trying to draw? Okay, let me get rid of my axis of rotation because it's not in the middle. Okay, here's the axis of rotation right here. Now let me draw a little outline. What does this kind of look like?
Circumference?
A disc. I failed.
Nah, I failed.
No, because this looks weird. Okay, so basically what we've done is the way you get the moment of inertia for like a disc, a rotating disc, is somebody who knows something about calculus would say, I'm going to apply this basic relationship that I'm just going to basically, and what I'm going to do is I'm going to just imagine that this disk of mass m and radius r consists of, okay, I'm definitely not going to draw all of them, but just consists of billions and billions of little tiny point particles. And there's, in calculus, this is called integration. You can do it, and we're not going to talk about it because, first of all, my calculus is very rusty and you don't need to. But let's look at what happens if we apply, all they're doing is adding up all the m's. Each one gets a little mr squared, mr squared. Of course, we're not doing it manually, they're doing it. And what you end up with is some values for actually kind of useful objects that we want to consider. I mean, objects that kind of look more familiar to us. For example, let's look at this disk. Okay, you've been looking at disks. You've actually seen disks on Pivot Interactives. Remember the students that, you know, they exerted torque on a disk, they got it rotating. Okay, so this would be an example of that rotating disk. This is the moment of inertia. Remember to see the capital I and the weird name, moments of inertia. Just think rotational inertia. And, oh, I'm moving it up. Oh, come on. Just trying to make it bigger. Come on. There we go. All right, so what are the things you need to know to quantify the rotational inertia of something large, like a, you know, rotating disk? Well, there's only two things. You need to know its mass, and you need to know its radius. You say, well, what about the thickness of it? Doesn't matter. Doesn't matter. Basically, this is the formula. Now, do you need to memorize that? Absolutely not. I couldn't remember. I mean, I see it now. I say, oh, the rotational inertia of a disk rotating through its center is 1/2 times the mass of the disk times its radius squared in meters. Okay, where does that come from? That comes from doing the calculus operation, which I'm too rusty to tell you, but basically through calculus, what somebody did was they just said, look, we're going to add up the individual moments of inertia of all the little particles that go into making up this disk. And okay, so basically, there you go. Now, what about a hoop? A cylindrical hoop. Well, that sure looks like a disc, except there's one huge difference. A disc, all the mass is distributed uniformly throughout the whole disc. With a hoop, and this would be the same mass, you have all the mass is concentrated at the outside. This would be like a bicycle tire if we could ignore the mass of the little spokes. Okay, now what would be its moment of inertia? mr squared. Now, you're not expected to know where these came from, but you're expected to know why does the moment of inertia of a disk, why is it bigger? Sorry, I meant why is the moment of inertia of a hoop bigger than the moment of inertia, the rotational inertia of a disk, when they have exactly the same mass and they have exactly the same radius? Yet the hoop has twice the moment of inertia. I think it's twice. Yes, see, I haven't memorized these. It's twice the moment of inertia. Now, let me pause the video. Okay, so let's go back to this, and I'm going to go ahead and erase all this because it's just getting in the way. So why does the hoop have a greater moment of inertia overall? Again, you're not expected to know why is the moment of inertia, the rotational inertia of a hoop mr squared. That's calculus. But you should be able to justify why the moment of inertia of a hoop is more than the moment of inertia of a cylinder that is of equivalent mass and equivalent radius. Because I hear you.
You want me to explain?
Sure.
I thought you were going to explain, but then.
Well, because it's so hard to get feedback here that I can, But sure, go for it.
In my other classes, teachers usually say, "What do you think?"
Oh, and then do they wait?
Well, if no one responds, they ask for questions, and if no one has questions, then it's weird. But usually, someone responds. Anyway, isn't it because all the particles on the circumference are farther away from the center, and thus every particle has to have higher force applied to it to complete that circumference?
Yes.
That same amount of time.
Yes, absolutely. The key thing you said there was the mass, the average position of mass, or the mass, the way the mass is distributed is overall further from the axis of rotation. The further mass is from the axis of rotation, the greater that mass is, that chunk of matter is rotational inertia. And that's it. I mean, that's the answer right there. When I see you on Wednesday, we'll look at some pictures of something called flywheels, which are things associated with engines, where if somebody wants to keep something rotating, if they want to have a lot of rotational inertia, you don't want to make a disc, you want to make a hoop, because you want to concentrate the mass as far away from the axis as possible. If you want to make something with a small amount of rotational inertia, you want to cram the mass in as close as possible to the axis of rotation, because that will reduce it. All right, what else do we have to do? Let's do a quick let's do a quick sample problem. A real quick sample problem to put this into context. All right, so let's do it. We have a hoop. Let's keep it simple. We have, not a hoop rather, we have a disc, and its radius is 0.5 meters. So R is 0.5 meters, and its mass, for some reason, when these formulas, they always use capital M, but there's no distinction between, it's just mass. Let's just say it's 5 kilograms. 5 kilograms, just made it up. And you exert a force of 10 newtons along the edge of it. Okay, so there's your R vector, and you can see that it's 90 degrees. All right, so what would be the angular acceleration caused by your application of a 10 Newton force on the outer rim of this disc. And we don't care whether it's accelerating. I mean, we don't really care. Let's just say it's not moving, okay, when you first do it, although that's not going to affect our calculation. All right, so let's get the angular acceleration. Okay, what's the angular acceleration? Well, we need to add up all the torques and then divide it by the object's rotational inertia. The torque is pretty easy. You've got 10 newtons perpendicular to a radius of 0.5, right? So that's going to be a 10 Newton force acting 0.5 meters. Oh, 0.5 meters. Now, what about this rotational inertia? This is a disc. Okay, so now we go look it up because you're not expected to memorize it. And this is in your textbook, and it's also available like in 89 places on the internet. So this is a disc. What is the moment of inertia of a disc? 1/2 times the mass times the radius squared. I'll just put that over here. 1/2 times the mass times the radius squared. All right, so we put in 1/2. We put in the mass, I said was 5 kilograms. And the radius of the disc is 0.5 meters, and we square that. And then you get a result. Okay, on top, creates that, your force creates a torque of 5 Newton meters. And then what's all this on the bottom? Well, I've got, okay, boy, I've got 0.5 times, that's 0.25. So that's a quarter, oh, that's an eighth. What is an eighth of 5? What is 5 divided by 8? Shoot. Somebody help me out. What's 5 divided by 8? Or let's put the 2 on top.
5/8.
Yes, it's 5/8. All right, so we put the 2 on top. That would double this. So, so what is 1/4 of 5? Is 1.25. Oh my goodness. Let's just come up with the answer. All right. What is 5? What is 10 divided by 1.25? That's going to be 8, right? 8. I think. 8 radians per second squared. Okay, that was completely sloppy, but I think that's how it works. Anyway, get out a calculator if you want 0.5 Newton meters divided by 1/2 times 5 times 0.5 squared. There you go. I think I did it right. All right, 10 times 0.5 is 5, but then what is 5 divided by 1/2? That's 10, and then what is 1/4? 0.5 times 0.5 is 1/4 of 5. Yes, I think that's correct. Anyway, there's the answer. All right, so that's Newton's second law for torque. You've got Mastering Physics that will ask you to practice these concepts and apply them. I'll be around tomorrow. Stop by if you have any questions during second period, third period, or fifth period.